I'm recording this and okay. Um, so yeah, uh, good morning. Thank you guys all for being here and hope you're all doing well. Oh, and I guess if at any point I tried to remember if it looks like I'm not sharing something, if it looks like my slides aren't changing or anything like that, please let me know. Um, today we are going to do lecture 7. We're basically going to finish our chapter 4, like energy dependence stuff today. And we're going to talk about something called slowing down theory, which is basically like the math behind understanding the slowing down process of neutrons. So I wanted us to kind of do some reflecting because we're at the point where we've seen everything like that every type of thing I can ask you, you've kind of seen as far as like you've seen homeworks, you've seen quizzes, you've seen exams. Hopefully after exam 1, we're feeling okay about that. I think that if you are staying on top of the homework and on top of the class, if you're doing the homework yourself and you're understanding the homework, then the exams are probably, we're hopefully pretty straightforward. Um, the homework is how you learn the material. So there's like that's the main way that you are building your knowledge, and then the quizzes and the exams, those are assessments, and so those are assessing the knowledge that you've obtained through being in the class, but also through like doing the homeworks and things like that. Part of why I'm bringing this up, it's not to I'm not like putting anybody on blast. I'm not like, you know, this isn't like an intervention or anything. I just wanted to make some comments because I did receive some concerns about like how long the assignments, like how long the homework and stuff like that is taking. Um, and I went back and I did the math, and I wanted to show you guys this math just so that you can appreciate kind of the way that at least this was my understanding is that so if you have a 3 credit hour course, like this is a 3 credit hour course, normally a semester is 16 weeks. And so the rule of thumb for like a 16-week semester is that you're spending 2 hours of outside class time for every 1 credit hour you're taking per week. So like what that means is that in a normal semester, you would be spending about 6 hours per week on your work, and then you have six outside of class on each class that's a 3 credit hour class. So that works out to like 96 hours per semester if it's a normal 16-week semester, but we don't have 16 weeks, we have 10. So that works out more to like about 9.6 hours per week. And like, it says minimum here. It kind of depends. It depends on what the class is. Some classes you could spend less than this and get an A in the class. So it's not necessarily a minimum. It kind of depends on the class, but I think for a hard class like new in 304, we should be probably spending at least about this much time. So if you're taking about 8 to 10 hours on average to do the homework, you're like right around what you would expect for a 3 credit hour course that's like a hard course. Um, so it's a summer course. It moves fast. If we have concerns about the homework, I have some recommendations for how we can make that go more efficiently. But based on this, I don't think I'm gonna adjust the length of the homeworks. And I hope that that makes sense. But then I also just wanted to talk about um, what I recommend in terms of like doing things more efficiently. And part of the way that I teach this class is based on what I know from like physics education research and education research in general. So like when I'm setting up a class, I know that students are going to learn when you have opportunities to think and write and question and respond and get immediate feedback. So that's why I set up my classes the way that I do. That's why I try to give you guys opportunities to write and respond to questions and ask questions. And Planning my lessons does take a lot of time too, and every lesson that I prepare takes about 10 to 15 hours. So I'm putting in my time and I'm putting in my work to make sure that the class is good and make sure that we're holding up our part of the a bargain too. And part of that is just like first being actively involved with the class. Because if you're involved, if you're staying on top and you're thinking about what's happening, then ideally if you're doing that, then once you leave class, you're like primed to be able to start the assignments that we have. And this is true that like if you are in a class and you are staying on top of it, then once you leave the classroom, you're at like a very important point where it's a very good time for you to begin trying to apply the knowledge that you've just gained while that material is still like fresh in your mind and not like waiting. The more that we wait after class to start the homework, the more that we're going to forget what we were covering and the harder it's going to be to get started. And I have things set up so that after, like, for example, after today's class, we should be able to do about the first half of this week's homework. And so after class, try to start the homework, try to solve or at least attempt every problem that looks like what we've already covered, so that whenever you show up to class on Thursday, you've already got a decent starting point, or maybe have already made like decent progress on the homework itself. And at that point, you're going to have questions along the way. Everybody's going to have questions, and that's okay and that's expected. And part of the benefit of starting sooner is that inevitably, when we get questions, we're able to get them addressed sooner versus, if we're doing the homework, say, Friday or Saturday or Sunday, then it becomes a lot harder to get questions answered because we're already pretty close to the deadline. So like going through this process for the Tuesday class, repeating it for the Thursday class, coming to those Friday help sessions, I recognize that a lot of us have other things going on, and so like if we aren't showing up to those sessions because we can't, then I understand. But if you are having a hard time with the class and you are available during those Friday sessions, please show up. I think you would find them very useful, and they're going to be more useful if we are showing up having made some progress on the homework. That means our questions are going to be more pointed, and that means that we'll get more out of those help sessions if we've started the homework. If you're showing up and you're struggling and that's why you haven't started, like that's okay. But making sure that we have made progress along the way, or at least attempted to make progress, had questions answered and that sort of things. I feel like if we are doing these things, then maybe if it takes us, if we aren't doing these things, but if we adopted some of these strategies, the homework takes 10 weeks, 10 hours to do before we adopt some of these strategies. Maybe the homework takes a little bit less time if we're doing something that's a little bit more efficient. So that's how I would try to approach it. I recognize our schedules might make this a little challenging, but th these are just some things that I hope you would consider. And that's enough for me ranting and rambling. And thank you for listening. And yeah, so getting into today's topic, which is slowing down, I wanted to just like kind of briefly review some of the things that we had talked about before we had our exam. So one of the big equations that we derived was the energy dependent version of our diffusion equation. This guy is like very similar to the one group diffusion equation. It just includes the fact that our scalar flux actually does depend on energy. So each of these quantities is a energy dependent reaction rate density. That means that because the scalar flux is an energy dependent scalar flux, it picks up an extra per unit EV units in the bottom. And for example, the fission spectrum is like a probability density and energy. So it has 1 over EV units. Similar story with this differential scattering cross section. It also has a probability density function attached to it with per EV units. So if you look at the units of each of these terms in the equation, it actually has units of neutrons per unit volume, per unit time, and per unit energy. So it's a reaction rate density per unit energy. So that's what each of these terms like physically would be telling you about. If it has these units, then like this first term would be your net leakage rate density per unit energy. You could also call that like an energy dependent net leakage rate density. But yeah, we just want to acknowledge that if it's an energy dependent problem, then our scalar flux is energy dependent, and therefore each of these terms is actually a density both in space and in energy, and it's a rate because it has those per unit time units. Um, we did, so that was the equation that has E as a variable, but then we said it's also possible and actually easier if we, instead of having the energy be a variable, if we just discretize a E so that we have a bunch of energy groups, and then we do diffusion calculations within each individual group. Each group has an energy range, and we kind of average all of our material properties and things like that. We just average them over each energy group. Um, and so ultimately, what we did was we got this equation right here that was our multi-group energy dependent diffusion equation. So it's like we took the energy dependent diffusion equation and then we averaged it so that it looks kind of like our regular one group diffusion equation, but we have a equation for every energy group, and we have some extra terms, these scattering terms that arise because you can have neutrons from one energy group scatter into another energy group. So this blue summation represents the downscattering term. The red summation represents the upscattering term. And if you so basically this is how our if you go back, this uh in scattering integral gets replaced by this summation. And then this summation has three terms within group scattering, down scattering, and up scattering. So we kind of replace the in scattering integral with these summations. We group the total cross section and the within group cross sections together, and that gives us this removal cross section. And then also we did a similar thing with the fission production term. We're also rewriting it as a summation as well. Um, so this is what the multi-group diffusion equation looks like as an equation. And then we can also recognize that this is in a form where we can write it as a matrix problem, where we've got a loss operator, we've got a production operator, and we've got the solution variable for each group. And this is just reminding us how we averaged the flux over each group. We basically defined each group flux as the energy dependent flux averaged over some energy group. So this basically is telling you about this is the flux of neutrons with normal flux units, neutron path length per unit volume per unit time. It's the track length rate per unit volume that are made by neutrons that have a energy within the group G. Um, and ultimately, when we got this equation, we were just using this definition and some clever use of the average to rewrite these the diffusion equation, the cross sections, the fission spectrum for each group, and nu f sigma f as group averaged values. So that's just to make sure we remember what we had talked about last time, and we're going to use some of those things. We're going to use a lot of that as we go into what we're talking about today, which is slowing down theory. So we've already talked a lot about how the behavior of a neutron population is going to depend on how those neutrons are being produced and how they're being lost. We know that those production and loss rates are either going to be neutron nucleus interactions, like fission or absorption or scattering, where we need the scalar flux. We also know that one of the big loss mechanisms is leakage, which we need the net current density for. We've studied how these different production and loss mechanisms are set up in various situations. And every time that we've had a different situation, we've written a conservation equation, and then we've said what are the gains, what are the losses, and we've expressed all of those terms for each situation. So that was how we got those like energy dependent diffusion equations. That was how we got the multi-group diffusion equation. And we are going to use those to better understand the energy dependence part, understand some of the math behind moderating neutrons or slowing them down. And this is going to help us better understand moderation, what kinds of materials make good moderators, and how to understand that phi of E spectrum that we had seen before. So this is that phi of E spectrum that I was talking about. We've seen this plot. We already kind of know some of the physics behind it. Like we have a peak in the fast region because this is where neutrons are born. Most neutrons from fission are born fast, and this part of our energy dependent flux looks like the fission spectrum. Um, in the thermal range, we have a peak at low thermal energies because as neutrons slow down, when they become thermalized, it means they're in thermal equilibrium with the atoms and the molecules in the moderating material, like in the coolant of a light water reactor or in the graphite of a graphite moderated reactor. So these neutrons, if they're in thermal equilibrium with their environment, they have a distribution that looks like the Maxwellian, which is the thing that it's a distribution that characterizes kind of like the vibrational energy of atoms based on their temperature. And as neutrons go from fast to thermal, fast is like around MeV range, like the average the most probable energy from fission is like 1 MeV, and then this thermal energy range is like 0.025 EV. So for a neutron to go from fast to thermal, it has to lose a lot, like 99.999% of its energy to become thermalized. And today we're going to basically understand that process in more detail, understanding the slowing down process. We'll also explain and kind of justify mathematically why the phi of E spectrum looks like the fission spectrum at high energies and looks like 1 over E in intermediate energies. So this is our energy-dependent diffusion equation. If we have a bare homogeneous reactor, um, if the reactor is homogeneous, what does that mean? What does that mean about like the materials? What does that mean about the dependence on our materials? Homogeneous means like same everywhere, right? So if something's homogeneous, that means it's like all made of the same material. And um, yeah, so just a quick question about exams. Yeah, I'm gonna have the exams. I'm about 30% through, and I'm gonna try to have those for you probably sometime like by the end of next week. Um, so in terms of homogeneous, that means that the material is the same. And so, no problem. You're welcome. And that means that whenever we write our cross sections, like the total cross section, it doesn't depend on position if the material is homogeneous. And if it's a bare reactor, that means that it's surrounded by vacuum. And if it's surrounded by vacuum, then we know that at our extrapolated boundary, we know that the value of our flux at that extrapolated boundary for any neutron energy has to be equal to 0 if it's a bare reactor. That means it's surrounded by vacuum. So this equation right here is our energy-dependent diffusion equation as an eigenvalue problem. And let's think about what this equation, like the kind of equation that this is. It's a differential equation because we have the Laplacian of the scalar flux. So we have like second derivatives with respect to space. The flux itself is a function of position and energy. So it's a partial differential equation because the flux depends on the solution that we're trying to find, depends on multiple variables, but it also contains integrals. We've got an integral, we actually have two integrals over the incident neutron energy E prime. And E is the energy of the neutrons that we are considering. Um, so this is technically a partial integro differential equation. And if it's a partial differential equation, we and we want to try to solve this equation, what we're probably going to try is the thing that's worked before, which is separating variables. So like we're going to assume that our flux, which is a function of position and energy, we're going to assume that we can write this as some function of space and some function of energy. So this is just like the separating of variables that we saw when we did like time dependence, where we had a space part and a time part. Here we have dependence on space and energy. So we have like a spatial shape function that only depends on the position. And then we have an energy distribution function that only depends on the energy. And just like we did before, we're going to plug the solution into our equation, and then we're going to basically try to manipulate the equation so that we get everything that has a function of energy on one side and everything that has a function of position on the other side. And so if you plug this in and then you rearrange it so that you get everything as a function of space um, on the left, notice that here the left side depends only on space or on position. And the right side contains only terms that depend on energy. This is a nice thing. This is like what we always hope to see when we do separation of variables, is that we get everything, one side that only depends on one variable, and the other side only depends on the other variable. So if we think about what this means, R, R is a variable. Like maybe it's a spherical reactor, so R goes from like 0 to whatever that extrapolated radius is. So we could, if we knew what this shape function is, we could evaluate the left side of this equation by just plugging in different values of R, like R equals 0, R equals 1, R equals 2, R equals 3. And as we're plugging in values into this left side, notice that the right side doesn't depend on R. So every single time that we're changing a value over here, changing the value of the input R, what's happening to the right side? Can the right-hand side change if it's a function of energy and we're only varying the position? It can't, right? This right side is going to be unchanged if we're changing the position. And if we're changing the position R, and the right-hand side of the equation is not changing, that means that the left-hand side of the equation can't be changing either, because the equations, it's an equal sign. The left-hand side and the right-hand side are equal. And I can make a similar argument with the energy. I could only vary the energy, like I could evaluate this at different values of the energy E, and as I changed the energy, the left-hand side isn't going to change because the left-hand side only depends on position. So if you have a equation where the left side depends on one variable and the right-hand side depends on another variable, that's only true if both of these sides of the equation are equivalent and they have to be equal to a constant. So um, that's kind of what we're seeing here. And this is what we're going to do is we're going to call that constant bn squared, just like we have done before. So um, if we just if we think about it like that, then we can actually take this equation that we have right here and write it as two separate eigenvalue problems, where we have one problem that's a function of space and is equal to that constant, and we have another problem that's a function of energy, but they're both equal to that same constant. And if we rewrite the space equation by just getting it into this form, so like multiplying both sides by the spatial shape function and then moving everything to one side, we get this as our spatial eigenvalue problem. And then on the energy side, this is what our equation looks like. And if we do some manipulating to get this term right here by itself, then what we're going to end up doing is multiplying both sides of the equation by f and by d. And then we're going to also move this sigma t term to the other side. and then we are gonna do some algebra. But basically, what we're gonna end up with on the left-hand side is d of E, the energy dependent diffusion coefficient, times our Bn squared plus sigma T of E. And then this whole quantity is being multiplied by F of E. So that's what you would get if you were to rearrange and basically isolate these two integral terms. And so now that we have these two separate eigenvalue problems, we can approach them separately. And so that's what we're going to do. When we see the spatial problem, hopefully we are recognizing this as something that we've already seen, that hopefully we can recognize this as our favorite Helmholtz equation. And we've already solved this one, right? So congratulations, we already solved the spatial problem. We're done with like half of it. We already know that the smallest of those BNs is going to be the eigenvalue that we associate with our fundamental mode and the multiplication factor. We know that that smallest Bn is called the geometrical buckling, and we call that Bg squared. So hopefully we didn't forget everything that we talked about in exam one, because unfortunately we are going to keep using all that stuff as we move forward. Um, So we've kind of already seen this before. We know that the space part, and specifically this buckling term, that if we looked at like the bucklings for the sphere and the slab and those different reactors that we've studied, we know that the buckling depends only on the reactor's extrapolated dimensions, like its size and its shape. Like if you think about for a sphere, then BG squared was pi over R tilde squared. So that's what we mean when we say this quantity, BG squared, it only depends on the extrapolated dimensions of the reactor. And that means that it technically mostly depends on material properties, but it actually does slightly depend on geometric properties. Sorry. It mostly depends on geometry, right? It mostly depends on the extrapolated dimensions, but it does have a slight dependence on materials. And that's because the extrapolated distance, so what we would be saying is that R tilde is like the real radius of our reactor plus some little extrapolated distance d. And we've made some approximations about that extrapolation distance. We've taken from transport theory that extrapolation distance is about 2 times the diffusion coefficient. And we've been assuming that diffusion coefficient is 1 over 3 times sigma transport. Or it's sigma t if you don't know information about sigma transport, but that's the more accurate way to define it as 1 over 3 times 3 sigma transport. And so this sigma transport is a material property, and it's inside of the diffusion coefficient, which means it's inside of the extrapolation distance, which means technically it's inside of our extrapolation dimensions. But if this is a reactor, these dimensions, whatever the value of R is going to be much bigger than whatever our extrapolated dimension is. So, in that sense, the extrapolated radius is going to mostly be based on the geometry and is only slightly going to be based on the materials. So hopefully that makes sense. The smaller the reactor is, like the smaller the value of big R is, then the more this buckling would end up depending on the material properties of the reactor. But for most like big reactors, the big R is much greater than the extrapolation distance. Therefore, the extrapolated radius is mostly determined by geometry. So that was the spatial part. We already know what that looks like. We already know that in the spatial world, we have all those fundamental mode eigenfunctions and the corresponding buckling for each geometry. So now let's take a look at the energy dependent problem. And if we look at this energy dependent problem, it actually is a balance equation that if we think about the left side, we can think of the left-hand side as kind of representing like the losses. Like the diffusion coefficient times the buckling is kind of like a net leakage term. And then the sigma t times, and both of these are being multiplied by this, by our like space, by our energy distribution function. So these aren't exactly like reaction rate densities, but we can think of these terms as being associated with the gains and the losses. This would be net leakage. This would just be like our total interactions. Obviously, this integral that has like nu f sigma f in the fission spectrum, that's going to be relating to like our fission production. And then the scattering term, the term that's telling us about neutrons scattering from some energy E prime into our energy E. This is like our in scattering term. So notice this energy dependent problem is kind of like a balance equation where we've got like losses on the left side and we've got gains on the right. Let's see. Oh, thank you. This is just interactions. So let me total interactions. Yeah, sorry if that wasn't clear. Whenever we and you might be wondering like why is the total interactions a loss term? Technically, like any interaction could knock the neutron out of our energy E. Like the obvious way is that if this is an absorption, any absorption is going to knock a neutron out of our group. But so yeah, it's basically just any interaction that results in the neutron being knocked out of the energy group E. Um, so this is a homogeneous equation. That means every term in the equation has some multiple of f of E. Um, and if it's a homogeneous equation and f of E is a solution, it means we could take any constant times f of E, and that's also going to be a solution. So if we solve this equation, f of E is only going to tell us about the energy distribution. It's not going to tell us about the amplitude of the distribution. Um, and so basically what that means is that we can normalize the distribution in a way that makes sense. Like we're going to basically kind of normalize to one, but we're not just going to normalize the distribution to one. We're going to normalize this whole quantity to be equal to one. And if we do that, mostly it is a convenient way to simplify the equations, because if we normalize this whole quantity to one, then we know that this term that was here is going to simplify. Whoops. This term here is going to simplify, and if this whole part is equal to 1, then all we have left here is just the fission spectrum. And so this is what we can refer to as the slowing down balance equation. And just to go from the top one to the bottom one, we're just substituting in this definition, this normalization condition into this above balance equation. And right here, I'm just showing you the equation number in Dr. Svedkov's notes, just so that we're making sure that if you are like maybe confused about this or wanting to look more into it, that you know kind of how this translates to what's covered in Dr. Svedkov's notes. Um, and just to make an important thing, because we care about units and we care about like what each term in our equation is representing, when we make this normalization, we just have to be careful that this chi of E is now like an effective source term that this thing is normalized to one. This equation, this right here is normalized to one, but it has units. Technically, if you look at this term, it's going to have units of inverse energy. I'm sorry. If you look at I mean, we could just look at the units. So nu F sigma F is like inverse centimeters. And then if this energy distribution has units of 1 over energy, and dE also has energy units, then overall, this normalized quantity actually does have some units of like inverse centimeters. So that means that chi of E, like this chi of E right here, technically has units of inverse centimeters and energy, right? Chi of E already by itself has units of inverse energy. And then as we go to this form, it's kind of picking up an extra centimeters, inverse centimeters, because of this normalization condition having some like units that are baked into it. So hopefully that makes sense. And now that we have the equation set up in this way, we can attempt to solve it. And in some simple cases, we can solve it. Um, Basically, what we want to do is like only look at the equation in certain energy ranges and then analyze the equation and the involved physics within those ranges. And so, like, as an example, if we look at just the fast energy range, then, like, talking about only neutrons that have energies above, say, like 100 keV, then we can rewrite the equation in this form, where this source is like a n-scattering source term. Um, and the reason that we do this is because if E is a energy that is very high, like above 100 keV, then we could probably make the argument that most and recall that like for a neutron to gain energy in a collision, it has to collide with something that's more energetic than it. Neutrons don't really collide with themselves, and to the extent that they do, we ignore it in all of our calculations. So a neutron's only going to collide with a nucleus, and the only way that the neutron collides with a nucleus and loses energy is if the nucleus, sorry, rephrase. If the neutron collides with the nucleus, the only way the neutron gains energy in that collision is if the nucleus had more energy than the neutron did before the collision. But if the neutrons have an energy of 100 keV, they are moving so fast that there's basically very little chance that they're going to collide with something that's going to kick them to a higher energy level. So we can basically make the argument that this n-scattering term is relatively low for neutrons above 100 keV. So like relative to this fission spectrum term, this n-scattering source term is like basically negligible. And if the reactor is very large, then how does that going to affect BG squared? Like if we think about BG squared for a sphere, then it's pi over r tilde squared. So if the reactor is very large, if R is very large, what does that mean about BG squared? It means BG squared has got to be pretty small, right? BG squared has got to be small if the reactor is very large. And that means that if we compare the diffusion coefficient times BG squared to the total cross section, if the reactor is large and BG squared is small, then that means that this BG squared term is going to be very small, so the total cross section is going to be much larger than the D times the BG squared. And therefore, effectively, what we're arguing with these two assumptions is that this term, the n-scattering term, is going to go to 0, and this term is also going to go to 0. So that means that all we're left with is total cross-section times our energy distribution equals the fission spectrum. So if we move everything to one side, then our energy distribution looks like 1 over sigma T of E times that fission spectrum. So recall that this is only for E over 100 keV. But notice that this actually agrees with what we were seeing in our phi of E plot, right? At high energies, when the energy is like above 100 keV, our energy distribution basically looks like the fission spectrum, and it just has a multiplier of 1 over sigma total. Um, so I told you that I would help us show why parts of the distribution look the way that they do. This is how we can show why the fast part of our spectrum looks like the fission spectrum. Um, so hopefully that makes sense. Hopefully that's making us feel a little better about that plot that we saw before, and not just like I'm making stuff up, but that we could actually kind of rationally understand why that could be the case, and logically show it with math. So that's how we can think about the fast energy range. To think about what that distribution looks like in the intermediate range, or in the slowing down range, we need to talk about the dominant way that neutrons lose energy, which is through scattering. And when we think about scattering, we basically just, I think about like kind of simple, like physics one billiard ball collisions, and it actually is a pretty helpful model to understand what's going on. Um, in any scattering process, like the neutron colliding with this nucleus, what kind of physical laws, like conservation laws, do you think that the scattering process has to obey? The physical laws that would govern like a two-body kinematics problem. And hopefully from like physics one, we have alarm bells in our head that are going off for things like conservation of momentum and conservation of basically the total energy. The only thing that makes these collisions slightly different than like simple billiard ball collisions is that we do have some quantum mechanical stuff peeking its way through. Sometimes these interactions result in um, you know, new if you have a nuclear reaction, then you can't just conserve energy. You have to conserve total energy, like the mass energy. You have to balance your E equals MC squareds and all that stuff. Um, but it's basically conservation of momentum, and really it would be linear and angular momentum. And in terms of like the main types of scattering, there's kind of, I think we can lump scattering into basically three big groups. And hopefully, like in physics, you probably talked about two of them, elastic, and then we have the opposite one, which is inelastic. Any I cannot spell. Oops. Inelastic. And also potential. Um, So those are kind of the three main groups that we can lump scattering into. Potential scattering involves Potential scattering is actually kind of similar to elastic. It's just that the neutron scatters off the potential of the nucleus without actually like interacting with the nucleus itself. Um, and so these are all defined in the book in a lot of detail. I'm going to today talk more about elastic and inelastic, because those are the main ones that are involved in the slowing down process. So in terms of like thinking about it like billiard ball collisions, elastic and potential are the two situations where that's like the most where that model is the least inaccurate, let's say. And so if we have an elastic collision, one of like the hallmarks of an elastic collision is in terms of the kinetic energy of the system, that in elastic collisions, the kinetic energy of the particles is conserved. Which, obviously means that like if you look at the kinetic energy of the particles in the initial state before the collision and in the final state after the collision, that the kinetic energy is the same, right? We had one MeV at the beginning, and then we have one MeV at the end if we total up the energy of the nucleus and the energy of the neutron after the collision. Um, and elastic scattering is like the main scattering mechanism for most nuclei. Oh, excuse me. It's the dominant scattering type for most nuclides and for most neutron energies. So if you think about it like a billiard ball collision or like two particles colliding with each other, then we can use that analogy to understand what kinds of things a neutron could collide with that would make it lose a lot of its energy, and what kinds of things a neutron would collide with that would make it lose very little of its energy. So think about a marble being kind of like a neutron, and like a basketball or maybe even like a bowling ball is like the thing that's kind of like in our analogy the nucleus. So if I take a marble and I throw it at the basketball, the basketball is stationary. I throw the marble at the basketball. What's going to happen? What's going to happen is that the marble is going to bounce off, and the basketball is like barely gonna recoil, right? So if the basketball barely moves, that means that the neutron didn't really transfer very much energy to the basketball. And that is a result of just the kinematics of that reaction and the basketball having a lot more mass. So if in a collision like that, the neutron is only losing a little bit of its energy if it's having a collision with a larger nuclei. If the nuclei is much larger than the neutron, then when the neutron collides with it, the neutron isn't going to lose very much energy. Just like when the marble collides with the basketball, the basketball doesn't gain very much energy. The marble doesn't lose very much energy. But now think about two neutrons, or think not about two neutrons, but maybe like a neutron is one marble and like a hydrogen atom is the other marble. Right, because a hydrogen atom and a neutron are similar mass, similar size. So if a marble collides with another marble, then if one marble is stationary and I take the other marble and I throw it at the stationary one, they're both gonna bounce off of each other. They're both gonna have like a comparable amount of energy after the collision. So that means that the initial neutron is gonna have transferred quite a bit of its energy to the smaller nuclei. So if a neutron collides with a smaller nuclei, then the neutron can lose a lot of its energy in that collision. And we're going to show this, but I just wanted to talk about this like using this analogy, just thinking about like marbles and basketballs, we can draw this conclusion, but we're going to show the math too. And in doing that, we're going to better understand like what makes a moderator a good moderator and how elastic scattering works. And it's elastic scattering that's doing most of the moderating or slowing our neutrons down in a reactor. So the other big type of scattering is inelastic scattering. If it's an inelastic collision, then the kinetic energy of the particles is not conserved. In your like physics one class, um, in an inelastic collision, the kinetic energy might not be conserved if like there's one object gets damaged in the process and then some energy goes into like deforming one of the objects, or maybe there's heat involved and so some of the energy gets lost as heat. Um, in an inelastic collision, the kinetic energy is not conserved and some of the energy goes somewhere else. In this case, of an inelastic collision involving a neutron and a nucleus, the extra energy goes into the nucleus becoming excited. So, like, if this initial energy has one MeV, and then after the collision it collides with half an MeV, the nucle oh, sure. This is supposed to be E of the nucleus. So the neutron has zero 0.5 MeV, the nucleus has zero 0.3 MeV, and then the remaining 0.2 MeV It's like contained within the nucleus as excitation energy. And so this nucleus is exciting, it's like vibrating around, and eventually it's going to settle down, and energy is conserved in that process. And as that nucleus settles down, it's going to emit a particle or more than one particle. And those particles, the particles emitted by the nucleus are gamma rays. X-rays come from electrons changing their orbital levels. Gamma rays come from nucleons in the nucleus changing their like nuclear energy levels. Um, so that's how energy gets conserved there. Um, when you have inelastic scattering, it's more likely to happen with high Z nuclei. So like, uranium-235, uranium-238, lead, things that are high on the periodic table, but also with high energy neutrons. And so inelastic scattering becomes a challenge for fusion reactors because so like for fission, the average neutron energy is about like 1 to 2 MeV. For fusion, it's about 14 MeV. So a fusion reactor has neutrons that are like an order of magnitude on average more energetic than fission neutrons. And like shielding fission neutrons is no joke. Like you could make a whole career just out of designing shields for fission reactors because fission neutrons have a lot of energy. They cause a lot of damage to materials. That is like happening on steroids in fusion reactors because the neutrons are so much more energetic. That means that in these collisions, in these inelastic collisions, they become more likely. The nuclei that are interacting with these high energy neutrons get very excited because they're interacting with neutrons that have a lot of energy. And then these excited nuclei are emitting a lot of very high energy gamma rays. So you both have to deal with the shielding, like in a fusion reactor. You have to both deal with the shielding of high energy neutrons as well as shielding of all of these extra gamma rays that are being produced because you have a lot more inelastic scattering. And this is a little paper, like I want to never test you on this or anything, but like if you're interested in fission, if you're interested in fusion, if you want to better understand like why are all of the reactors fission reactors and why has fusion taken so long and what are the challenges with fusion? This is a good thing to just be aware of. Um, so getting more into understanding elastic scattering, um, the analysis, you basically have to do kinematics and um, It's 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 essentially just our physics one conservation of momentum and conservation of energy. But for these neutron nucleus interactions, it's the math becomes a lot easier if we use something called center of mass coordinates. And that means that we set things up using coordinates where the center of mass of our system, of the interacting particles, is considered to be at rest. This is called a center of mass system. Center of mass system. And when we set up this center of mass system, we're going to have a neutron with some mass little m, and we're going to have a target nucleus with some mass big M. And the lab frame is like the frame that you would be used to if you were thinking about this problem. If you were thinking about a neutron colliding with a stationary nucleus, this is how you would draw the diagram, just kind of like I drew the diagram here, right? That's what we would probably think of if we're thinking about this in like the lab frame. Um, in the center of mass frame, you set the problem up so that the center of mass is at rest, which you can do this transformation. It's perfectly valid. You just have to make sure that you do everything kind of consistently. So like instead of this target nucleus to achieve this, one of the things that you have to set up in the problem is that both objects are actually moving towards the center of mass frame. Um, so the center of mass frame is a little bit different. What we have to do in this process of going to a center of mass frame, we'll define some quantity called capital A, and this just represents the ratio of the nucleus mass to the neutron mass, right? The target nucleus is big M, the neutron mass is little m. And this is like approximately the atomic mass of the nucleus. Technically, the neutron mass is not exactly one, so that's why this is approximately the atomic mass. If you're doing calculations to find big A in like a real reactor, um, you want to actually find the mass of the particle and the mass of the neutron and calculate it this way. But if it's just a calculation in my class, I don't care if you approximate A as just the atomic mass of the nucleus. Just be aware that for these scattering, for elastic scattering calculations, if you ever see a big A and you think it's an atomic mass, the more precise thing is it's actually probably a ratio of the masses, and just in calculations, you can usually get away with making it the atomic mass because it's very close approximation. But like if you're designing a real reactor, there's no reason to not just use the more accurate or the more precise kind of definition. Um, and if you set this problem up and you go through all the kinematics, it's going to look like, kinetic energy and momentum before, kinetic energy and momentum after. The neutron in the center of mass frame ends up with this deflection angle, which is the theta c. And so if you do the math, this is the expression for the final energy of the neutron coming out of that collision. And the final energy of the neutron only depends on its initial energy, the deviation angle in the center of mass frame, as well as this parameter called alpha, but alpha is actually just defined based on this parameter big A, and alpha is big A minus 1 over big A plus 1 quantity squared. So notice that alpha only depends on the ratio of the mass of the nucleus to the mass of the neutron. Um, and then this final energy, it just depends on what that ratio is. It depends on alpha, and it also depends on the deviation angle theta c. Um, I will not ask you to like memorize or derive this. The derivation is in the book. And I mean it's not terribly complicated, but I don't think we need to spend our time in class deriving this equation. But we're gonna take this result and we're gonna get some understanding out of it. Um, so just making sure that we're defining all of our terms. EF is the final energy of the neutron, so like after the scattering event in the lab frame. EI is the energy of the neutron before the scattering event, also in the lab frame. So in the lab frame, again, those are the values that we're used to. So this equation is in a nice form where the final and initial energies are already expressed in the lab frame. And then this theta angle, the deviation angle, it is defined in the center of mass frame. And ultimately, that's okay for us because where these theta values are going to come from is experiments. Those experiments are already going to be done in a center of mass frame. So it's like we take the experimental value for theta c, and then we use our own lab values for EI and EF, and everybody's happy. Um, so if we take this equation, we can figure out what's the maximum energy that a neutron could have, and the corresponding angle that would go along with that maximum energy, right? Like if the final energy depends on the angle, then whatever the scattering angle is going to dictate what our final energy becomes. And so if you think about like scattering, where I've got my neutron and I've got some big nucleus, the neutron has a mass of m, little m, and then this is the nucleus, and it has a mass of big M. if the neutron is going to scatter off of this nucleus and lose the most amount of energy, um, sorry, I guess I want to think about this differently. I want to think about what's the maximum energy it would have after the scattering event. So if the neutron comes in, scatters off the nucleus, what final angle for theta c would correspond to the neutron having the most possible energy after the scatter? It starts with energy EI, and so if we scatter off of something and we want to have the most possible, and by the way, the nucleus is at rest. So like there's no way that the neutron is gaining any energy from the nucleus. We're just thinking about in the scattering event, what final angle is going to give the neutron the most energy after the scatter. And hopefully we can just reason, like we can just think about that from like just thinking about kinematics, particles colliding with each other, and we could recognize that 0 degrees would be the angle that would correspond to the neutron losing the least amount of energy, right? Because if it's 0 degrees, it's like the neutron just basically grazes right by. So and that's what we would call that kind of collision. We would call it a graze. And if you plug in 0 for theta c, then you have cosine of 0, which is 1. And then inside of the brackets here, you have 1 plus alpha and 1 minus alpha. So the alphas subtract off, but then you get 1 plus 1, which is 2. And then the 2 here can cancel this 2 here. So that means that the final energy, if theta is 0, is the initial energy, right? And that's kind of like what we had talked about when we mentioned like the differential scattering cross section before, that the way we'd think about it is like we send neutrons in and then we measure their energy after. And if the neutron gets sent in with some energy EI and it's colliding with nuclei that are like basically stationary, then the best that the neutron can do from conservation of energy perspective is just have the same energy it had that it started with. Um, and that's going to correspond to 0 scattering angle. Now, the other thing that we could ask is what way can the neutron collide where it's going to lose most of its energy or the maximum amount of energy? And if coming in and then basically not changing my direction was how I kept all of my energy, well, then it kind of stands to reason that the more that my angle deviates, the more energy I am going to lose. And the most possible that I could deviate is if I was coming in at 0 degrees, well, the way that I would lose the most energy is if my final direction was in the exact opposite direction, which would correspond to theta equals 180 degrees. So that would correspond to a backscatter. And if theta is 180 degrees, then cosine of theta is -1. And so then what happens in here is that now this alpha becomes positive and this 1 becomes negative. Like the sign on these two terms switches. So then the 1's in here will subtract away. The alphas will add together. I'll have 2 alpha here. I'll have a 2 in the denominator. So this is going to give me alpha times EI. So the minimum energy that I could have is going to be alpha times the energy that I started with. And we know how to calculate alpha. So if we want the minimum energy to be very, if we want the neutron to have a minimum energy here, then that means that alpha should be very small, right? If alpha is a small number, then we're going to have a small number multiplying by the initial energy, and that's going to make the final energy as small as it could be. And for alpha to be small, this is our definition of alpha. So for alpha to be small, what do we need to say? What has to be true about the capital A, which we can kind of think of as the atomic mass? It means that the atomic mass should also be small, right? Like if A for hydrogen, if A is about 1, then alpha is 0. And if A is 2, then we have like 1 over a half, 1 over 3 squared. So you have like 1/9. So like the smaller value of A, the smaller the value of alpha. So A, big A, should be small. And that agrees with what we had said just before about the whole, like, this is the idea of like, if the neutron is a marble and it wants to lose a lot of energy, it should collide with another marble. It should collide with another particle that is about the same size as that nucleus, if we want the neutron to lose a lot of energy in that collision. And we had talked, so like just kind of reviewing, we had talked about differential scattering. We set this up because there is a distribution of neutron energies after a scattering event, just like we can see here, right? The neutron is going to have a variety of scattering angles, which is going to correspond to a distribution of the final energies. So this is a probability that it's a cross section, the differential scattering cross section, this guy right here, that has the EI to EF. When you see the EI to EF, it means within this quantity, we have baked in a probability density function that tells you about the probability of the neutron scattering from some energy at EI to some final energy EF. And now we know that that probability is kind of also going to have to do with that deviation angle theta. So what we kind of need is to understand both how the energy of the neutron and the scattering angle of the neutron are what this probability looks like based on the energy of the neutron and based on the scattering angle. And I have some really interesting plots that can show us that. So these are some probability density functions of a couple important nuclides in nuclear engineering. So the way that we think about these plots is that the the vertical axis is a probability per the cosine of the scattering angle, but basically you can just think of it as a probability. The cosine, this is telling you about it's the cosine of the scattering angle. So if the scattering angle is 0, um, then cosine is +1, so that corresponds to like a for like the neutron just going through the material. If theta c is pi or is 180 degrees, then the cosine of theta is a -1. So along this line right here, that corresponds to forward scattering. And along this line right here, where cosine of theta c is -1, that corresponds to backscattering. And then, if theta is 90 degrees, then that's cosine of 90 is 0. So that middle line corresponds to the scattering angle being 90 degrees. And then along this energy axis, this is showing how this distribution changes for the energy of the neutron, for neutron energy EI. So hopefully that kind of makes sense, that we can look at different neutron energies, and then we can look at these plots to say, what's the probability of a scattering occurring, and that the scatter results in the neutron coming out with some angle or having some scattering cosine. So this first one is for hydrogen, and notice that the plot is flat for every single neutron energy, and what that basically shows is that in the center of mass frame, hydrogen is an isotropic scatterer. The angle here has an equal probability. There's an equal probability that this resulting angle could be anything between 0 and 180 degrees. So that's why we say that hydrogen is called a perfect S wave scatterer. This is if you hear somebody referring to a scatterer being S wave, this is the kind of plot that they're talking about. And they're saying that for any neutron energy EI, the resulting scattering distribution has equal probabilities of having, there's an equal probability that that neutron comes at at a given angle. So hydrogen is important because that's a big moderator, right? All of our light water reactors use water as a moderator, and it's mostly hydrogen that's participating in that moderating process. Here's carbon-12. And so it's the same exact plot, but for different nuclides, you get different distributions. And um, so notice that for carbon, it is basically an S-wave scatterer up until around this energy right here. This is like around 2 MeV. And notice that past a neutron energy of 2 MeV, this guy starts doing really weird stuff. Some neutron energies, the distribution becomes forward peaked. At some neutron energies, the distribution becomes backward peaked, and it kind of oscillates back and forth between one and another. This whole region is weird stuff. This is like weird quantum mechanical. If you want to understand what's going on, you got to understand a lot more than I do about quantum mechanics. But that's basically what's going on. And I mean, luckily for us, 2 MeV, that's beyond most neutron energies that we deal with fission systems. Um, but yeah, so notice that if we have carbon, which like if we talk about a graphite moderated reactor, then that's mostly carbon-12. And notice that carbon is also basically an S-wave scatterer up until about 2 MeV. Here's oxygen 16. You know, water is like hydrogen and oxygen. So oxygen is also an important nuclide. Notice that it is also basically an S-wave scatterer until we get around 200 keV. And then once the neutron energy is above 200 keV, again, we start seeing weird stuff and oscillating between forward and backward scattering and things like that. But up before 200 MeV, it's about an isotropic scatter. Basically scatters the neutrons um, with an equal probability in every direction. And here's uranium-238. So uranium-238 is interesting because like, so it also, once you start to get around, say, I guess it's around here, like around 50 keV, it starts to deviate from S wave scattering, and uranium-238 is just an interesting one that it's like mostly forward peaked. It's a mostly forward peaked scatterer at high energies. Um, so hopefully those plots make sense. The first time I saw these plots, I thought they were so cool. And I think it helps, like if you can think about this plot, it helps to better understand what we're talking about when we talk about like different scatterers having certain this is what we're talking about when we talk about those distributions, both in terms of like energy and in terms of angle. So if something is an S wave scatterer, that means that the scattering is isotropic. That means that there's no preferred orientation of the neutrons that get scattered off. There's an equal chance that they have a given energy after, sorry, there's an equal chance of them having a given angle after the scatter. So this right here is what the probability density function looks like for an S wave scatterer. So like if you have hydrogen or if you have a nuclei that can be approximated reasonably as an S wave scatterer, which we just saw that for like all of the nuclides that we saw, if we were between like 1 and 50 keV, it basically was S wave, right? It was basically those distributions were flat. So we mostly, oops, damn, sorry. We mostly see S wave scattering if you're like less than 50 keV. Um, and so, oops. So for S wave scattering, it's isotropic. This is like the most common scattering that you'll see in nuclear engineering. And basically what this is showing is that you if the scattering is isotropic, then the energy distribution is also constant. That for a given scattering angle, and that was like, every pot looks like a square if it's S wave, and that's kind of like what we're seeing here. Um, that you have equal distribution of the outcoming energies as well. As long as my energy is within EI to alpha EI, the probability is constant. Um, so we like S-wave scattering because it's simple and it's like the only case that we can deal with analytically. And so now we can actually approach this for a simple case, and we can look at what the slowing down distribution is going to look like for the simple case of an infinite medium of hydrogen. So if it's pure hydrogen, then we can say that that atomic mass or that ratio of the nucleus mass to the neutron mass is basically one. Um, for hydrogen in the slowing down range, it's basically a perfect scatterer. That means that the sigma total is basically just the scattering cross section. It has basically no absorption cross section. Hydrogen is very small, so it's not going to do inelastic scattering. It's basically a pure elastic S-wave scatterer. That means that the scattering is going to be isotropic. Um, we assume that no neutrons have some upper energy E sub zero, and that's just like, whatever the max neutron energy is, like say 10 MeV, we could set the cutoff there, or 2 MeV, we could set the cutoff there pretty reasonably as well. Um, and that's basically true for fission reactors. And if it's an infinite medium, then we can say that Bg squared goes to 0. Um, and so we're going to start with these kind of simple assumptions, and we're still going to be able to learn a lot from doing this. Um, so if we calculate alpha for hydrogen, if A is 1, then in the numerator we have 0 divided by 2, and that means that alpha equals 0 for hydrogen. And so hopefully we can see that there's going to be terms in our equation that we can simplify based on those assumptions. Thank you. So a good question, Thomas. So Thomas is wondering, how is deuterium even a thing if what we're saying is that hydrogen basically doesn't absorb? We're basically being we're only looking at the slowing down range. So we're kind of only considering like that intermediate range from, let's say, if I go back to my if we think about the slowing down range, we're kind of saying like, let's say from here to here, right? So that's the slowing down range. So really what we're saying is that it is true in these energies. And if you so to answer your question, if you were to look at the sigma A for hydrogen, it is not non-zero outside of that range, but it's basically 0 in the slowing down range. Off the top of my head, I don't remember if it's fast or thermal neutrons where it is more likely to absorb, but that's what you would find. If we have some time after I get through the rest of my slides, I'll pull up Janice and we can take a look at that. Um, so if we take those assumptions, then we can simplify our scattering PDF. No problem. Thank you for the question. We're saying that for hydrogen, oops, we're saying that for hydrogen, alpha is 0. So therefore, this probability density function actually looks really nice. It's just 1 over EI. And I guess just to see where I simplified in this next equation, we can just start crossing stuff out here, right? So if it's an infinite medium, That means BG squared goes to 0, so we could cancel out this term. Notice that my sigma t, this is basically going to become sigma s of E because of assumption number 2. And because of the assumptions that we were making about uh, S-wave scattering, that's going to allow us to simplify how we define this probability density. So hopefully that makes a little bit more sense how we're going from here to here. And so that's all we've done is we've made those simplifications into our equation, and we are integrating now from the energy that we're considering, the energy of interest. So this is basically integrating from all energies that we're considering up to the maximum possible energy that we're interested in. At this point, because both sides of the equation have a product of sigma s times the energy distribution function, and notice that we also have that here, then we're going to define the collision rate density, big F of E. This is the general definition for big F of E, for the collision rate density. But because sigma A is 0, then in this case, the sigma T becomes a sigma S times our energy distribution. And so in terms of the collision rate density, if we plug this definition of the collision rate density into this form of the slowing down balance equation, chi of E is unchanged. The left side becomes the collision rate density. And then here, we're still integrating. So we still are integrating from E to E sub 0. The integration is still with respect to dE prime. And now we're just going to have F of that E prime over E prime. So that's what the slowing down equation becomes if we assume that it's an S-wave scatterer, and that the total cross-section is basically just the scattered cross-section. And from there, so this is where what oh, okay, sorry. Um, I wanted to make sure I didn't like lose a slide or something. So essentially, I am skipping some steps, and we're just gonna be a little hand wavy, and we're gonna say that that previous equation can be solved analytically. And then if we were to solve it, this is what we would end up with. So ultimately our goal is to like get a solution for f of e, and this is what that solution would come out to. We have some difficulty here because, oh shit, this is supposed to be big f of e. I apologize. So, right, big f of e is the thing that we are trying to solve for. This is complicated by the fact that we have f of e here, but it's also inside of the integral. And so the analytical solution to that equation is this equation. And this equation can be rewritten back in terms of the energy distribution function if we just divide both sides by sigma s. So if we do that, then big F of E is returned to little f of E. We're dividing both sides by sigma s now, though. So we're going to have chi of E divided by sigma s of E. And then we're going to have a plus. This term is also the 1 over E here is going to pick up a factor of 1 over sigma s. So we're going to have 1 over E times sigma s of E, and then our integral. Sorry about that. Um, and the next thing that we're going to basically argue is that within sorry, we're just going to assume that if this chi of E is our fission spectrum, then it's basically like only valid in the fast range. Like if we say it's only valid between some E star and our maximum E, that means that if we say E star is like 100K, if E star is like 100 keV and our maximum considered energy is like 10 MeV, then the fission spectrum is zero outside of that range. It's basically zero if it's describing like the production of mostly fast neutrons. So if we make that assumption, then we can basically write our slowing down equation for three different ranges. The range for any energies above our considered energy, for neutrons with energies that are in like kind of the fission spectrum range of about 100 to 10 MeV, and then any neutrons with energies that are like less than E star, so like less than 1,000 keV, but are still within the slowing down range. So because the fission spectrum, or actually because E0 is our cutoff energy, then for any energy above E0, there's no distribution. For the energy range where the fission spectrum is valid, then this is the form, and it's valid over this energy range from E star to E sub zero. And then this distribution is also going to be what we have for the other energy range, for the range below E star. We just have to ask the question, how does the integral simplify if now, based on the definition, our, oh, and so notice how going from here to here, outside of the E star to E0 range, the fission spectrum is zero. So when we go to this part, there's no chi. Chi equals zero in this range. So it's just this term. The integral on our term, the bounds on that bottom integral is basically just uh, from E star to E0, and that's because E can be anything less than or equal to E star, but the fission spectrum itself is going to be non-zero for any E that's less than E star. So we just set this to be E star. The maximum bound is still E0, and this we're effectively integrating a probability density function over its entire domain. And if we integrate a probability density function over its entire domain, we know that that is going to equal 1. So this whole integral is 1, and then what we're left over is just this multiplier on the side. So it's a 1 over E times a 1 over sigma s of E. So notice that in the slowing down range, the distribution, our energy distribution looks like 1 over E with a multiplier of 1 over sigma s. And 1 over sigma s is basically constant in the slowing down regime. So that's why we basically say that in the slowing down regime, that the energy distribution follows 1 over E. Um, so yeah. So that's what I wanted us to see in terms of going through the math of basically solving the slowing down problem for hydrogen in an infinite medium with no absorption. It's like a good model because it's simple enough that we don't have to do like any crazy calculations, but it also gives us a lot of the meaningful results that we were seeing. And you know, if the result was more accurate, like if we were considering a more realistic problem, The result would change, but the overall form of these distributions would not change. Basically, you would kind of just have a different multiplier. And if you got more detailed, for example, in the slowing down range, you could get more detail with a kind of multiplier slash a function that is in a way accounting for some of the resonances that we have in the slowing down region, right? The 1 over e plot that we're getting is not telling us anything about those resonances because in the model that we just did, we haven't included any of that physics. And if you were to include the physics, you would still see a similar distribution, but it would look more complicated because you would be solving a more complicated problem. So hopefully that makes sense and helps us feel better about understanding that plot. Um, Now that we have kind of said all of that about energy dependence, we're at a good point to introduce a very useful quantity in nuclear engineering called lethargy. And we use the symbol little u for lethargy, and it is defined as the natural log of some E0 over some E. So E0 is defined as a reference energy. We basically just kind of like in the previous problem, we set E0 to be whatever our high energy cutoff is for our reactor. 10 MeV, 2 MeV, somewhere in the several MeV ranges where we'll set E0. And then E is just the kinetic energy of the neutron, and it could vary from E0 to 0, right? E0 would be like the maximum, and then 0 would be the minimum. Um, and we use the lethargy scale because it simplifies math and it is very useful for doing slowing down calculations. So it also kind of agrees with what we talk about with the neutron life cycle. So think about when the neutron is born, its energy is at a maximum. So the energy E is approximately E0. So if the energy E equals E0, then we have ln of 1 and ln of 1 is 0, right? So the lethargy U is 0 when the neutron energy is at its maximum. And then because of the form of this function, as E, the neutron energy gets smaller, the lethargy goes up. Um, so the U, if you think about the form of this equation, U, the lethargy, increases as E decreases. So lethargy follows the kind of life cycle of the neutron, and that neutrons get more lethargic as they slow down. As their energy decreases, their lethargy increases. Um, and so if you want to get the change in lethargy is just the final minus the initial. And then we define the lethargy based on the definition, where the only thing that we vary is what is the final energy we're considering. E0 is always the same reference energy. So this would be my final, this is my final lethargy, this is my initial lethargy. We can use properties of logarithms to rewrite that, and that's how we got here. This is how we can express the change in lethargy. And if we take this definition of lethargy and rearrange it to get E, the neutron kinetic energy by itself, you should get E sub 0 times E to the minus U. And that's just taking the exponentiating both sides and then getting the kinetic energy E by itself. So with these definitions, we have a way that we can do a change of variables from quantities of energy to quantities of lethargy. So like if we wanted a reaction rate density and energy, we could convert it into a reaction rate density and lethargy. And then because lethargy, notice that lethargy is dimensionless because we're going to end up doing ln of E over E. And the E's, like if it's electron volts, the E's on the top and bottom are going to cancel. And the natural log is a dimensionless quantity. So energy, if it's energy dependent, it has per EV units. If it's lethargy dependent, it doesn't pick up any per EV units because lethargy is dimensionless. And if we want to convert a quantity from energy to lethargy, we just have to make sure that we're conserving any relevant physics in the conversion process. So like if we want to rewrite the collision density from energy to lethargy, what we have to conserve is the collision rate density. Like in other words, really what we're saying is we have to conserve the collision rate density. So if there's a collision rate density of a certain number of collisions per unit volume per unit time, whether we're writing that as a density in energy or whether we're writing that as a density in lethargy, they have to be the same. They have to be describing the same number of collisions per unit volume per unit time. So definitionally, this would be the collision rate density in energy, and this would be the collision rate density in lethargy. And there's a minus sign in front because of the fact that the energy and lethargy go in opposite directions. That is, E goes up, the lethargy goes down. If we take this expression and rearrange it, then if we get f of e over f of u, then we would also divide both sides by dE. So this would look like negative du over dE. And we have u as a function of energy. Like we have a definition for lethargy. So if we, I'm going to plug that in right here because we know that u is ln of E naught over E. And if you're doing the derivative of a log, this might look intimidating because you have ln of something divided by something, but recall from properties of logs that ln of E0 over E is just ln of E0 minus ln of E from like properties of logs. And we're taking the derivative of this whole thing with just respect to E. And E0 is a constant. So if you're trying to take the derivative of this, it might look more complicated than if you try to take the derivative of this. Because if we take the derivative with respect to E, this first thing is just a constant and its derivative is 0. And then if we're taking the derivative with respect to E of negative ln of E, well, hopefully we know that if we integrate 1 over E, that we get a log. So if we differentiate ln of E, we get 1 over E. And there's a minus sign here, but there's also a minus sign in our equation. So ultimately what this is going to look like is just 1 over E. Hopefully that tracks. Hopefully we can follow that. And so if that is the if f of e over f of u is 1 over e, then it follows that f of u, our collision rate density in lethargy, is just the energy E times our collision rate density in energy. All we're doing is taking this expression and like multiplying both sides by f of u and multiplying both sides by e. So that's how we can write the collision rate density in lethargy as in terms of the collision rate density in energy. Um, and the scalar flux, the lethargy, the scalar flux as a function of lethargy also is going to have a very similar definition. It's going to look like E times the scalar flux as a function of energy. And that's because when you do that conversion process for the scalar flux, you have to do the same thing. You have to conserve your reaction rates. Um, However, if we want to write a cross section as a function from a function of energy to a function of lethargy, there is no 1 over E multiplier in that conversion process because sigma is not a density in energy. Therefore, you don't end up with that 1 over E when you do the conversion. You can basically just directly convert the energy to lethargy, and then it's like, if I know for every energy, I get my corresponding lethargy by using this equation, right? If I know if I just use the definition of lethargy, then for every energy E, I can get my corresponding lethargy, and then I can just map these cross sections 1 to 1 to say, if I knew what my cross section was at a given energy, then I know that my cross section is going to have the same value if I just use the same the lethargy that corresponds to that energy. The other thing that's really important is basically, so if we know the lethargy gain per collision, then we also and we know the average lethargy gain per collision, then we can actually start doing some really useful calculations. We had already defined that the lethargy gain, U final minus U initial, is the lethargy change, but also by definition, it's the lethargy gain. And it's the same as the logarithmic energy decrement because of the definition of Ln, that this is the same thing as Ln of EI minus Ln of EF. Um, so um, this is the okay, so sorry. What we have right here is just the lethargy gain per collision. Now, the average lethargy gain per collision is another quantity. We call that worm, or you can call it squiggle, but people will look down upon you if you do that. And it's the Greek letter xi, which looks like a worm. Also, it kind of does look like a squiggle. But so this is the symbol worm, and it represents the average lethargy gain per collision. And so it's basically like if you think about this is the formula for lethargy gain, worm is just the average of that. So it's like we're taking a weighted average of the lethargy gain, and it's weighted to the probability density that a neutron scatters from the energy EI to the energy EF. Um, and this is a quantity that you basically can't evaluate it analytically unless you have a very special case and you can come up with a nice expression for this probability density function. And the special case that we have is S-wave scattering. And so if we take that probability density function, we sub it into the definition of worm, then we get a complicated integral that can be solved. Technically, this is solved with U substitution, but I'm going to call it X substitution here because U is another quantity, the lethargy. So if you do X substitution of the following, then you can rewrite the integral in a form that's easier to solve, and then you can get an expression for the average lethargy gain per scattering collision for an S-wave absorber. So this is a formula that we can use to compute how much lethargy a neutron gains in a collision. And notice the lethargy gain per collision only depends on alpha, which means it only depends on that ratio of the mass of the nucleus to the mass of the neutron. And if we know basically, if we know the atomic mass of a substance, we could figure out the average lethargy gain per collision. We just have to assume that it's an S-wave scattering. And like we already showed, that's a decent approximation for most nuclei if they're in like the slowing down range and below the ranges that we were talking about. So with worm, we can start computing and getting and evaluating what makes a good moderator a good moderator. In general, it has to have a high value of worm or a low value of alpha to make the neutrons lose a lot of energy per collision. We want a high scattering cross-section so that collisions that give me collisions that result in the neutron energy decreasing happen with a high frequency. And we don't want our neutrons to be absorbed. So we also want our moderators to have a low sigma a low absorption cross-section, so that neutrons don't get absorbed or lost in the moderating material. And there's two definitions, like figures of merit for evaluating moderator effectiveness. The first one is the moderating power, which is worm times the scattering cross-section. And the other one is moderating ratio, which is worm times the ratio of scattering to absorption. And if you know worm, then which is the average lethargy gain per collision, and we also have a definition for the total lethargy gain, which is just ln of E0 over E final, then it follows that the average number of collisions to make a neutron go from the initial energy that it was born, E0, to the thermal energy where it gets absorbed or cause the next fission, EF, we can just divide the total lethargy gain by the average lethargy gain per collision to find the number of collisions that give us that energy or lethargy change. So this equation is very helpful if you want to know for a given material how many scattering collisions are going to be required to make it go from my fission energy to my thermal energy. All you need to know is what the fission energy is, what the thermal energy is, and what the atomic number of your scatterer is, so that you can get worm. Um, so that is everything that we need to be able to evaluate how good is a given moderator. And this is a table that gives some of those figures of merit for some common moderators. Um, this is from Adam's notes. There's a similar table in Dr. Svedkov's notes. And so notice that, like, if you just look at the moderating power, it can be kind of misleading because the moderating power might make you think that water is better than deuterium. Similar thing with the average number of scatters required to make you go from like 2 MeV to 1 MeV. It's less scatters in water than it is in heavy water. So we might, from these two metrics, be tempted to think that water is the better moderator, but the moderating ratio is the thing that gives us some extra context and includes the fact that we really care about not just do they scatter, but also what's the relative ratio of scatters to absorptions. And because absorption is a lot higher for hydrogen than it is for deuterium, deuterium ends up having a way better moderating ratio. So it's not all just worm and it's not all just the moderating power. We also need to think about the moderating ratio as well. Um, and that is everything that I wanted us to say about energy dependence. So that basically gets us through the end of chapter 4. And next class on Thursday, we're going to start chapter 5, and these are based on the Svetkov's notes. And chapter 5 is about heterogeneous reactors. So at this point, if you have any questions, please let me know. Our current homework is posted on Canvas as well as in our Google Classroom. Sorry, I feel like I'm back in high school. Our Google Drive. Um, then yeah, you have everything that you need to get started on that homework. And from what we've covered today, you should be able to get through the first a little bit more than half of it, actually. You might have noticed I posted your reactor design problem too. That's going to be due on the last day of class, which is August 5th. But after this week, we're going to be able to do and knock out the reactor design project. So I figured I would just post that today, and uh, give us extra time to be able to work on that. I'll talk more about the reactor design problem probably on Friday. It won't make as much sense until we cover tomorrow's class. So after tomorrow's class, I'll start talking more about that, the reactor design problem. But yeah, so homework 4 is up for you. The reactor design problem is up for you. And if y'all have any questions or need anything from me, please let me know. Otherwise, I hope y'all have a good rest of your day and a good day tomorrow. And y'all take care. And I'll talk to y'all on Thursday. I'll stay back for a couple minutes, so if anyone has any questions, we could talk about it. And otherwise, at this point, if you don't have any questions for me, then you're good to go. Have a good one. Take care, and I'll talk to y'all soon.
I have a question.
Hey, what's up?
So, unfortunately,